Dear students, today we are going to discuss about the mechanism of hydrogenation of olefins using Wilkinson catalyst. First, on passing hydrogen into the solution of the catalyst in benzene, followed by the addition of olefin, the alkane is going to be formed. Okay, for that process, we are now seeing the mechanism. Here, the L is a ligand and it is for simplicity mentioned as PPH3, that is triphenyl phosphine. You know what is Wilkinson catalyst? Wilkinson catalyst is tris triphenyl phosphine chlororhodium 1. In this diagram, you are able to see that there are 3 L. Okay, those L are mentioned or represented as tris triphenyl phosphine. First, let us look on to the step 1. In the step 1, in a less sterically hindered phosphine complexes, the catalytic effect disappears. As small ligands do not readily dissociate, which is essential for catalysis, they render the catalyst ineffective. In the corresponding iridium complex, in which the metal phosphorus bond is stronger, apparently no dissociation takes place and hence catalytic behavior disappears. So in the step 2, it is called oxidative addition. What is called oxidative addition? An oxidative addition is leading to the formation of a 5-coordinated species in which the oxidation state rhodium is +3, that is raised from +1 state of the rhodium. This step is an oxidation reaction. The coordination number of the central metal ion is increased from 4 to 5. Okay, therefore, you might have able to understand what is called oxidative addition. Oxidative addition is both involving the increase in oxidation state as well as the coordination number of the central metal atom. Okay, then hence this step is also an addition reaction. Since this step involves the both oxidation and addition, it is referred to an oxidative addition or reaction or Oxford reaction. Then let us come to step 3. Step 3 involves the coordination of the alkene to the potential vacant site on the 5-coordinate dihydrido complex to form the 6-coordinated species. In this step, the metal has not only weakened the alkene double bond by coordination, but has also brought the alkene and the hydrogen atoms into close proximity, where they react probably in a 2-step process and which can restart the catalytic cycle. In this step, the second role of the catalyst, namely the weakening of the bond between the 2 carbon atoms, is accomplished. Then let us come to step 4. Step 4 is an insertion reaction. It involves the insertion of olefin into metal hydrogen bond to give metal alkyl derivative. Okay, then let us come to step 5. It is the reductive elimination step. Reductive elimination step is the inverse of oxidative addition. Here, the metal rhodium is reduced from oxidation state +3 to +1 state, and coordination number of the central metal is decreased from 6 to 4. In this step, the product alkane is formed. Okay, in this step only, the product alkane is going to be formed. The third role of catalyst, namely the transfer of hydrogen fragments to the alkene, yielding the product of alkane, is achieved in steps 4 and 5. Now, let us discuss the advantages of Wilkinson catalyst. Advantages. Compared with the older process, which was likewise homogeneously catalyzed and marked by high reaction temperature of about 250 degrees Celsius and by pressures around 750 atmospheres, this new process operates under considerably milder reaction conditions. Then it is possible to selectively hydrogenate biologically active substrates such as steroids. The value of this catalyst is based upon the fact that hydrogens are transferred specifically to the cis position, not a trans position, that is, it is selectively used for cis position. Then last one, This catalyst is specific for the hydrogenation of terminal olefins due to steric reasons. Okay, there are in the second step and third points, we are able to conclude that this Wilkinson catalyst is selective for the hydrogenation of cis and terminal olefins. Okay, then let us come to disadvantage of the Wilkinson catalyst. Being a soluble catalyst, it cannot be removed easily at the end of the reaction by simple filtration. Due to this imperfect separation of alkane and rhodium complex at the end of the hydrogenation, rhodium is lost in practice, although the catalytic cycle shows no loss of rhodium. The separation of the catalyst at the end of the reaction is a major problem, and it is one of the reasons why industries have been unwilling to adopt homogeneous catalyst more widely. Because of the high cost of rhodium and the high cost of converting it into Wilkinson catalyst, this process is highly expensive, but however it is highly selective. Okay, in the lower classes you might have studied that hydrogenation. So hydrogenation under electrophilic addition. In those days you might have seen the catalyst. So what are all the catalysts you have applied for the hydrogenation of alkene? Yes, platinum, nickel and so on. Okay, but what is the substrate you are taking? That is the gaseous or liquid alkene. Therefore, the substrate and the catalyst were in the different phases, that is heterogeneous phases. Therefore, that type of hydrogenation were coming under the electrophilic hydrogenation, but in the heterogeneous medium. But here the Wilkinson catalyst is coming under the homogeneous medium, that is Wilkinson catalyst is readily soluble in the given medium, that is given organic medium. Therefore, we need not worry about the heterogeneous medium. Okay, but this homogeneous medium is now maybe giving some small headache, that this rhodium catalyst, since it is homogeneous, the unreacted Wilkinson catalyst or some reacted byproduct of Wilkinson catalyst may not be filtered. Okay, this is the only problem. Even if we want to recover the Wilkinson catalyst, that is causing more complicated work. So this is the only headache when we are applying the Wilkinson catalyst. But however, as I told already, it is the good selective catalyst for the alkenes to undergo the terminal olefin conversion of alkanes and selectivity on the cis position. Okay, thank you. Let us meet in the next video. Dear students, today we are going to discuss about the hydroformylation of olefins, the Oxop process. The most important example of homogeneous catalysis involving an organometallic compound is the so-called hydroformylation reaction. It involves the addition of hydrogen and carbonyl to a terminal alkene to yield an aldehyde. Thus, the net reaction is RCH-CH2 plus H2 plus carbon monoxide, that is carbonyl, gives the corresponding aldehyde. Since it is used to make oxygen containing compounds from hydrocarbons, it is also known as Oxop process. The importance of Oxop process, the technical importance of this reaction from the ease with which the primary Oxop product, the aldehyde, can be converted into a multitude of industrially important secondary products such as alcohols by reduction, acids by oxidation, or esters by allowing the alcohols to react with acids formed by the reduction and oxidation of aldehydes respectively. Some of these secondary products are useful as plasticizers, detergents, lubricating oils and solvents. Come on, let's go to discuss the mechanism of this hydroformylation process. Okay, step 1. Step 1 involves the generation of the active catalyst. You might have seen in the first step, that is, it is the formation of the active catalyst. Why I am insisting it is termed as active catalyst means we are having in the top of the reaction CO2 CO8 times. It is said to be a catalyst, but this catalyst cannot be used as a catalyst. Therefore, this catalyst must be converted into an active catalyst by the addition of hydrogen. Therefore, we will get HCO CO4 times from CO2 CO8 with hydrogen. So, let us come to step 2. Step 2 is the addition of alkene to the coordinatively unsaturated HCO CO4 times to form a coordinatively saturated 6-coordinated alkene pi complex. Step 3 involves the insertion of alkene into cobalt hydrogen bond to give an alkyl intermediate. Step 4 is the another insertion reaction, namely carbonyl insertion to give an acyl complex. Step 5 is the reaction of gaseous hydrogen with the acyl complex to yield an aldehyde and HCO thrice. Step 6 is the final step, and it is the rapid absorption of carbon monoxide, that is carbonyl molecule, by HCO thrice. Here you must able to differentiate CO is cobalt and CO thrice is carbonyl. Okay, let's continue to generate the active catalyst HCO CO4 times, which will restart again the whole catalytic cycle. Now let's move on to the defects, because we have seen the importance advantage in the previous. Therefore, let us come to the defects of this catalyst. This catalyst works well only at 150 degrees Celsius and at a pressure about 200 to 400 atmosphere. So it is looking very, therefore it is requiring very high temperatures and almost high pressures. Okay, usual normal atmospheric pressure is 1 atmosphere, but it requires 200 to 400 atmosphere. It is somewhat unfamiliar pressure controls. Okay, so only expert can only approach these plants. Okay, in order to manage 200 to 400 atmosphere. This necessitates the use of vessels which can withstand this high pressure and high temperature. Okay, so in order to handle this high pressure, it requires that kind of vessels to withstand this high pressure, otherwise they will be burst out. Okay, then this leads to the high plant cost for the industrial process. So in order to withstand and manage this high pressure, so this construction of plant requires very high cost, high expensive. This catalyst also catalyzes hydrogenation of olefin under these conditions. Hence, a part of the olefin is lost as alkane. Okay, here one more disadvantage is since we are taking the alkene, so this part of the alkene might be converted into aldehyde, but the remaining would be converted into alkane. Okay, so that's why it suffers from some type of defects, that is drawback. You may ask that, sir, what is the problem of getting this byproduct alkane? Okay, sometimes if we get alkane, this byproduct alkane may be mixed with that wishing product that is called aldehyde. Okay, sometimes they may be mixing both. They may be mixed both together. Therefore, it will be very difficult to separate them. Then volatility of HCO, so CO 4 times. Okay, the recovery of the catalyst, it says that the recovery of the catalyst, okay, the volatile nature, volatile means easy recovery, so volatile means readily evaporating. So this readiness of evaporating of this active catalyst requires more number of more quantity of catalyst. Then final drawback, since the addition of HCO CO4 times to unsymmetrical olefins can occur in two directions, and since HCO CO4 times can isomerize olefins under these conditions, it is not surprising that mixtures of linear and branched chain aldehydes and ketones are often obtained. Okay, if you are taking Wilkinson catalyst, in that Wilkinson catalyst we have not suffered this type of problems, this type of difficulties. Okay, it is only that the Wilkinson catalyst is used to hydrogenate selectively at the terminal position, but here in this Oxop process we are applying the given catalyst for hydroformylation, that is alkene to aldehyde, but sometimes we will get that, or sometimes that reaction will be end up with not only the alkene, so not only with the alkane, but also with the branched chain alkanes, and sometimes aldehydes and sometimes ketones. Okay, if these problems were not coming, then this will be the a good catalyst for the hydroformylation process. So that's all about the hydroformylation reaction. However, some modifications were characterized. Let me reveal that modification. Various modified catalysts have been described for increasing the yield of linear aldehydes. Tributyl phosphine and triphenyl phosphine substituted cobalt carbonyls and rhodium complexes have been tried. Of these modified catalysts, the most important is the rhodium catalyst. Okay, this hydridocarbonyl tris type of rhodium complexes was also discovered in Wilkinson laboratories. Okay, thank you. Let's meet in the next video.